guys, this is Brandon Ronk,
and Megan Brooks.
and we're here to talk to you today about fatty acid synthesis. And the first thing that we're going to address is just the overall reaction of fatty acid synthesis. As you can see here, it takes the acetyl-CoAs and combines them to create a palmitate group. And what it does is it also reduces the NADPH into NADP+, as well as ATP into ADP. This reaction also produces water and inorganic phosphate, as well as regular coenzyme A groups.
Alright, the overall mechanism. A 16-carbon fatty acid is formed through reacting with fatty acid synthase, which occurs in the cytosol. This reaction is mitigated by acyl carrier protein, which carries the fatty acid chain throughout the reaction. Fatty acid synthase is a multi-enzyme complex that catalyzes all reactions discussed in the actual construction of the fatty acid.
The integral enzyme in all of this is fatty acid synthase. As you can see, there's a picture of it. It has 5 different enzymes on it, and as the reaction progresses, the molecule is going to move from enzyme to enzyme on this complex. Now, fatty acid synthase 1 is common in vertebrates and fungi. This is the one that humans utilize. It only creates a single product with no intermediates, a single 16-carbon saturated fatty acid. And FAST2 is used in plants and bacteria. Unlike FAST1, FAST2 can form a variety of products and is more efficient as an enzyme.
Alright, and here are the abbreviations that you saw on the last slide. We're going to talk about them throughout the presentation. Also, some coenzymes required for the fatty acid synthesis are NADPH, ATP, manganese, biotin, bicarbonate, and acetyl-CoA, which you'll also see throughout the presentation.
On this next slide, it's going to have a general picture of the reaction. This is kind of useful because as we go through each of these reactions and their enzymes and all the byproducts and everything else, we want y'all to have kind of a general idea of what is happening and what is going on with the molecule itself. So if you need to refer back to this slide to kind of see the structure as we progress, that's probably a good idea to keep yourself oriented.
Alright, one of the first things that we need to do for fatty acid synthesis is the creation of malonyl-CoA, which is formed by the carboxylation of acetyl-CoA and bicarbonate via acetyl-CoA carboxylase. This step is tightly regulated as the enzymatic activity of acetyl-CoA carboxylase is affected by insulin and glucagon as well as other factors. Acetyl-CoA carboxylase utilizes biotin as a prosthetic group to carry carbon dioxide, similar to how pyruvate carboxylase operates. Manganese is also used as a cofactor for the carboxylase as well as zinc.
Now, the main step of the reaction that's regulated and what keeps the reaction regulated as a whole is the regulation of acetyl-CoA carboxylase. And the three things that do it are insulin, which works as an activator, and then glucagon and epinephrine deactivate. Now, all three of these act by covalent modification to achieve their activation and deactivation. There's also allosteric activation that occurs from citrate, which is a product of the TCA cycle, and increases the Vmax of the enzyme. And there's also regulation to prevent an overabundance of fatty acid synthesis, and this occurs by palmitoyl-CoA acting in a negative feedback loop for the reaction.
Alright, next will be the joining of acetyl-CoA and malonyl-CoA with the acyl carrier protein. The enzymes that do this are acetyl transacylase and malonyl-CoA. The ACP that has been mentioned throughout the slide stands for acyl carrier protein, which serves as a stabilizer for the fatty acid as it moves from one enzyme to the next.
The next step in this reaction is the condensation of acetyl-CoA and malonyl-CoA into acetyl-acetyl ACP, and one of the other products is carbon dioxide. This is catalyzed by beta-kevacyl ACP synthase. The decarboxylation of the malonyl group facilitates the nucleophilic attack of the methylene carbon, which allows them to combine to each other. Therefore, the reaction is highly exergonic, making the reaction thermodynamically favored. Because it is thermodynamically favored with a large negative, it gives energy, it is going to not be a regulatory step at the reaction.
Alright, the first reduction we're going to talk about is the reduction of the carbonyl group, which produces a beta-3-hydroxybutyl ACP. And the enzyme that does this is beta-ketoacyl ACP reductase. This enzyme creates a stereospecific D product, which has a cis-steric orientation. And we're going to reduce an NADPH to NADP+.
The next step is going to be dehydration, and this is catalyzed by the enzyme beta-hydroxyacyl ACP dehydratase. And the product that is produced is trans delta squared butanoyl ACP and water.
Alright, the second reduction is reduction of the double bond, which produces a butyl ACP, and the enzyme that does this is enyl ACP reductase, and we also reduce another ADPH to ADP+.
And following the reduction of the double bond, the reaction is going to repeat itself from condensation to reduction of the double bond. And what it's going to do is transfer the butyl group from the phosphopantothene to the cysteine thiol group of beta-ketoacyl ACP synthase. And the new group is going to replace the original acetyl group.
Alright, the ACP complex repeats the process of adding 2 additional carbons a total of 7 times until a 16-carbon saturated palmitoyl group is created. This repetitive cycle is not completely well understood, but it has been observed that this is the point where it stops. The palmitate is then released from the ACP by a hydrolytic activity of thioesterase.
Now, one of the diseases commonly associated with fatty acid synthesis is diabetes, and diabetes mellitus specifically. And diabetes is characterized by an underproduction of insulin, as we already discussed. Insulin is integral in the activation of acetyl-CoA carboxylase, which is the regulatory enzyme. So with a low level of blood insulin, the body is unable to simply store these carbohydrates as fatty acids and then further on into triglycerides and phospholipids. And thus diabetics often have issues with regulating blood sugar simply because they can't store them for long-term use. A lot of people think that obesity is a product of diabetes, but typically obesity precedes diabetes and is not a result of the disease. And this is due to the fact that diabetes simply cannot produce fats as effectively.
Fatty acid has a big part in homeostasis, since it's the first step in the formation of lipids, which allows humans to store energy for long terms, as well as providing us with thermal insulation. Our blood glucose regulation, without fatty acids, humans would be required to constantly have food supplies to keep a steady supply of glucose to the cells to create energy. The formation of fats allows intermittent fasts that can keep a steady blood glucose level. In the thermal regulation, without this fat formation, it would become more difficult as the environment has more impact on the surface blood temperature. Thus, cold environments would be less inhabitable.
We appreciate y'all listening to the slide or listening to our video. We hope y'all learned a lot about fatty acid. This is our sources where we got all of our information. Again, we thank y'all for listening to us.